Good morning, students. Welcome back to Signals and System online video lecture series. In this class, I am going to cover the four topics. One is mean square error, complete set. Next one is orthogonality in complex signals. Last one is orthonormal signals. From these four topics, one question will be asked for short answer question or a long answer question. So by reviewing the previous class, I am going to cover these four topics. In the review, we are going to discuss about the two topics. One is orthogonality in signals. Next one is orthogonal signal space. By reviewing these two topics, I am going to cover the four topics, and from that four we can expect the one question in the university exam. So in previous class we have discussed the orthogonality in signals, and also we have discussed the orthogonal signal space. So I am going to review these two topics. Orthogonality, nothing but when the two signals are perpendicular to each other, then that two signals are named as orthogonal signals to each other. When the two signals are perpendicular to each other, we can call them orthogonal signals. Perpendicular means angle between those two signals is equals to 90 degrees. For example, I am having the two signals such as f of t, it is a continuous time signal. X of t is another continuous time signal. So that we are saying that these two signals are orthogonal signals, so that angle between them is equals to 90 degrees. That means what? Here this is, assume that this is f of t and this is ex of t. This is a signal x of t and this is a signal f of t, and both are perpendicular to each other. That means angle between them is equals to 90 degrees. This theta is equals to 90 degrees. When the angle between the two signals are 90 degrees, then we can call them orthogonal signals. Orthogonal signals. That means what? Here this f is going in one direction and x of t is another signal, it is going in another direction, so that the f of t signal will not project, f of t signal will not, that cannot project any component along x of t, or x of t is a signal, it will not project, it cannot project, it can't project any component, it can't project any component along x of t. That means what? Like this it is going like, the f of t is going like this and x of t is going like this. In general terms we can say that f of t will not have the interference on x of t and the x of t will not project any interference along x of t, f of t. So this, when a signal is not at all projecting any interference along another signal, then we can say the both signals are orthogonal signals. This is the case of the orthogonal signal. So that in the orthogonal signals, f of t is not at all projecting any component along x of t and x of t is not at all projecting any component along f of t, so that the component c is equals to 0. In case of orthogonality, component c is equals to 0. That component we have discussed, that component c is equals to general formula integral t1 to t2. T1 to t2 is nothing but it is a time duration, integral t1 to t2 and f of t into x of t dt by f of t into x of t dt by integral t1 to t2 f of x square of t dt. This c is generally, if t is a theta is equals to 90 degrees, this c will be 0. If theta is less than 90 degrees, what happens if the theta is less than 90 degrees? That means what? F of t will be like this, so that the f of t will project one component, f of t will project a component along x of t or x of t will project a component on f of t, so that in such cases if theta is not equals to 0, that means what, theta is less than 90 degrees, then we can get the c is a non-zero value. If we are getting the c is a non-zero value and the given signals are not orthogonal signals, the condition for the orthogonal signals, c must be 0. That means angle between the two given signals must be equals to 90 degrees. In such cases, one signal cannot project any component along another signal. In such cases, c is equals to 0, but the c is general equation for the c is equals to integral t1 to t2 f of t into x of t dt by integral t1 to t2 x square of t dt. So in case of orthogonality, we are saying c is equals to 0. Here the c is we are having the formula, but it has to be 0. So to make it to 0, we have to go with some cases. Here if we can't make this denominator is 0, because we can't equate this denominator is 0, because denominator is an energy signal. Energy can't be a 0 within the given time duration. So that obviously to make c is equals to 0, numerator, that is integral t1 to t2 f of t into x of t dt must be equals to 0, so that we can prove the orthogonality between the two signals by proving the integral t1 to t2 f of t into x of t dt is equals to 0. If we prove integral t1 to t2 f of t into x of t dt is equals to 0, then indirectly we are saying that the given two signals are orthogonal signals. That means what, the given two signals are mutually perpendicular to each other. That the concept we have studied in the orthogonality in signals. Now we are going to review. I'm going to review the orthogonal signal space. Orthogonal signal space. In the first point, we have only two signals, f of t and x of t. But in case of orthogonal signal space, x of t is nothing but it is a set of signals. X of t is nothing but it is a set of signals. X of t, I am assuming it is a set of signal, that is x1 of t, comma x2 of t, comma up to xn of t. That means what? X of t may be here x of t may be x1 of t, x2 of t, x3 of t up to xn of t. Here all these x1 of t to xn of t are the mutually perpendicular to each other, so that in that cases when the more than two signals are orthogonal to each other, then that phenomenon is named as orthogonal signal space. When more than two signals are orthogonal to each other, we can call it is orthogonal signal space. In this orthogonal signal space, by making use of the orthogonal signal space, if you are using the three signals such as x1 of t, x2 of t, x3 of t, then we can form the three-dimensional signal space. If we use the four signals such as x1 of t, x2 of t, x3 of t and x4 of t, then we can form the four-dimensional signal space. Here it is having the n number of signals, so that we can form the n-dimensional signal space. In this n-dimensional signal space, any signal such as f of t can be represented. And any signal can be represented in that particular signal space, that is f of t, so that f of t can be orthogonal to the any signal within the signal set. That means what, f of t can be orthogonal to the x1 of t, f of t can be orthogonal to x2 of t, f of t can be orthogonal to the xn of t. If f of t is orthogonal to the any one of these signals, so that we know that the c is equals to 0. If f of t is not at all orthogonal to any one particular signal in the given signal set, so that c is a non-zero value, we can get c is a non-zero value. In that case, we will be having the formula, that is ci is equals to, that means what, if I am taking f of t along with the x1 of t, so that it will be the c1. If I am taking f of t and the next signal from the signal set I am taking x2 of t, so that it will be the c2. Likewise, we can have the various components by choosing the various signal from the signal set of x of t, so that ci is equals to 1 by ei is nothing but energy of that signal, integral t1 to t2, t1 to t2, f of t remains same, that is f of t into this. Now we are choosing any signal from this one, so that I can have xi of t dt. That means what? If I wanted to have, if I wanted to calculate the C3, if I wanted to calculate the C3, that means what? What I am choosing, f of t remains same. I am choosing the x of t signal is x3 of t from the signal set of x of t. So that now I am checking the orthogonality between the f of t and x3 of t. So that here that will be the C3 is equals to 1 by E3 is nothing but it is the energy of that x3 of t signal. Energy can be calculated as integral t1 to t2, that is x3 of t whole square dt. That means what? We can calculate energy like this, and integral t1 to t2 f of t dt into x3 of t dt. By calculating that one, we can get the value of ci. If in the case this xi of t and f of t are the orthogonal to each other, in such cases we can get the ci value is equals to 0. The point is very clear. If the two signals are said to be orthogonal, the angle between them is equals to 90 degrees. That means both the given signals are mutually perpendicular to each other. In that case, the one signal cannot project the component along the another, so that c is equals to 0. In order to make c is equals to 0, we can prove that integral t1 to t2 f of t into x of t dt is equals to 0 if we have only two signals. But if we have the more than two signals, we can call that is a orthogonal signal space. Orthogonal signal space can be defined between the more than the two signals, so that it can form the 3-dimensional, 4-dimensional up to n-dimensional signal space. In this n-dimensional signal space, we can represent any signal that is f of t. If that f of t is orthogonal to the any one of the signal of this signal set, then we can have the c is equals to 0. If this f of t is not orthogonal to the any signal in this particular signal set, then we can have the ci is a non-zero value, and that value can be calculated in the formula ci is equals to 1 by ei. Ei is nothing but the energy of a signal, integral t1 to t2 f of t into x1 of t dt. So now this is the review. This is the review of that orthogonal signals and the orthogonal signal space. Now I am going to talk about the another important thing, that is mean square error, that can be asked for 5 marks in the exam, so that it is very, very important. We can easily get the mean square error derivation if you are good at the orthogonal signal space and as well as orthogonality in the signals. Now let us consider the mean square error. Generally mean square error signal, we know that error signal is nothing but this is EE only. This is EE. EE is nothing but what? Integral t1 to t2 x square of t dt is nothing but it is an energy signal. It must be a finite value. It must be a finite value. But what we are going with? We are going with the mean square error. That means what? We are having the error signal, that we are going to have the mean square error. Mean square error is nothing but here, after knowing the energy of a signal, we need to divide that by, that is time duration, that is t2 minus t1, so that EE by t2 minus t1 is nothing but it is the mean square error only, and the mean square error is denoted with the E square of t bar. If it is a vector, then we have to calculate EE. After that we have to divide by t2 by t2 minus t1, so that will be the mean square error. So that we know that we know that EE, in the previous class we have studied the EE, that is nothing but E of t is equals to what we can have. E of t is equals to, we have the formula E of t is equals to, The general formula is what? F of t is equals to c into x of t plus e of t. From this e of t is equals to, we can write e of t is equals to, we can write f of t minus c into x of t. But here we are having the various values for the c and the various values of x of t, so that we are having the n number of x of t signals, so that we can have the n number of projected components by the f, and so that I can write this equation is what? F of t minus, I can write f of t minus sigma n is equals to 1 to n, because all these components are added together, so that xn of t into, and it is nothing but a Cn. Now we have what? EE we have EE. Then we have to, this is energy, this is the error signal. We have to calculate energy of that signal, that is EE. EE is nothing but energy of that signal. What is the formula of the energy of signal? We can directly write energy of signal integral T1 to T2, integral T1 to T2, and this is x square of t. Here in place of x square, what we have? This is complete total part, and so that I can go with f of t minus sigma n is equals to 1 to n xn of t into cn whole square and dt. Whole square and dt. Now it seems to the a minus b whole square, and a minus b whole square is equals to a square minus 2ab plus b square. In that way we can expand this expression by making use of the a minus b whole square, so that this is a and this is b. Now I am going with the what? First one is EE is equals to, this is energy of a signal. After knowing the energy of a signal, we have to go with the mean square error by dividing the EE by T2 minus T1. I am calculating EE only. EE is this is the formula. EE is nothing but, this is the formula in which x square of t is nothing but, this is total a signal, and we are squaring that one. Now EE is equals to, then a square integral T1 to T2, a square is nothing but what? F square t dt minus 2ab, 2 into integral T1 to T2, I can write T1 to T2 sigma n is equals to 1 to n, I can write Cn into xn, Cn xn of t into f of t. 2 a, f of t is a and b is nothing but sigma n is equals to 1 to n xn of t into Cn into dt plus what we can have b square integral T1 to T2, b is nothing but this total part, so that I can write sigma n is equals to 1 to n and xn square of t into Cn square dt we can write. Now interchanging the order of integration and summation, we are going to interchange the order of integration and summation to make the simplification of this signal, so that I am going to write this one. Here I am after interchanging the integration and summation, I can have EE is equals to, this is not having any sum term, so that summation term, so that I can write simply integral T1 to T2 f square t dt minus, here I am interchanging this one 2 into sigma n is equals to 1 to n and integral T1 to T2 Cn into xn of t into f of t dt. Here I can write Cn is also here, Cn is a constant, so that Cn will be outside, so that xn of t into f of t dt plus this is, I can write, I am interchanging this one, so that I can get the sigma term is outside, sigma n is equals to 1 to n is equals to 1 to n integral T1 to T2, then we can have here the Cn square is also the constant, I can take outside, and the remaining term is what? xn of t square dt. Then I am going with the another simplification, that is about, see this one here, this total term, this is EE is equals to, I can write, this is integral T1 to T2, I can write f square of t dt minus 2 into, then after making the integration of this one, what we can have? We can have this is what here 2 into, I can write sigma n is equals to 1 to n, and here this is what? Here this sigma integral T1 to T2 xn of t into f of t dt is nothing but, it is the energy of that particular signal only. So that here Cn I can have in this equation. Now we are having this remains same, 2 into sigma n is equals to 1 to n, and Cn remains same, and now we are having integral T1 to T2 xn of t into f of t dt. I can write this one, see here from this formula I can write Cn is equals to, this formula I am writing, Cn is equals to 1 by En integral T1 to T2 f of t into xn of t dt. So now this part is equals to what? Integral T1 to T2 f of t into xn of t dt is nothing but, it is a cross multiplication only. Cn into En is equals to integral T1 to T2 f of t into xn of t dt only. That means what? Integral T1 to T2 f of t into xn of t dt we can simply replace by Cn into En. That means what? I am simply replacing this term is Cn into En plus, then I can write this is as it is, sigma n is equals to 1 to n, this is Cn square, I can write Cn square, and this is nothing but integral T1 to T2 xn square of t is nothing but, it is the energy of a signal only, integral T1 to T2 x square of t dt. Here this is xn is there, so that energy signal is nothing but En. So that here now we are going with the differentiation integration. Now see this one, integral, I am writing integral T1 to T2, this is f square t dt minus 2 into, now I can write this is sigma n is equals to 1 to infinity Cn into Cn, that is Cn square into En, and my plus sigma n is equals to 1 to n Cn square into En. This second and third term remains same only. See this one, this is Cn sigma n is equals to 1 to n En square into En, and this is also sigma n is equals to 1 to n Cn square into En. This is minus 2, this is plus 1, so that we can subtract this one, so that here we can have what? Here we can have integral T1 to T2 f square of t dt minus 2 plus 1 will be the minus 1 only, so that I can write it is sigma n is equals to 1 to n Cn square into En. Then what it is? It is EE now, EE, but what we have to calculate? Mean square error is nothing but EE by T2 minus T1, that is nothing but mean square error. It is denoted with small e square of t bar is equals to, we can write that is 1 by, that is what? Here we are having this form, this one, and we can have 1 by T2 minus T1 of this total part. Now total part, that is the total part is what? Integral T1 to T2 f square of t into dt minus sigma n is equals to 1 to n Cn square into En. This is nothing but, it is the mean square error of that given error signal. So that I am going with the final expression, EE by T2 minus T1 is nothing but mean square error, and it is simply denoted with the E square of t is equals to what we have? Then we have EE is what? We have EE, that is T1 to T2 f square of t into dt minus sigma n is equals to 1 to n Cn square into En. but we have to divide that is by T2 minus T1, so that you can write it is divided by T2 minus T1. This is T2 minus T1. This is nothing but it is a mean square error. From the concept of mean square error, we can define one of the important point, that is a closed set or the complete set. See this one here. This is the mean square error. At one particular point, this mean square error is going to be 0. Whenever the mean square error is going to 0, that point is named as closed or the complete set. At what point it is going to 0? Because this n is always positive only, n is always positive only, so that as the n value increases, this term value is also increases, so that this term value is increases, then the most is going to be subtracted from this f square of t dt, so that as the n value increases, then this mean square error value is going to decreases. At one particular point of n value, this e square of t is going to completely 0, and that case, that is named as complete set or closed set. Now I am going to define this closed set or complete set. In this equation, Cn square into En is always positive, hence the error energy can be reduced. Hence the error energy, this is error energy, can be reduced as the Cn and En value increases. That means what? Hence error energy, that means what? This is EE, that is error energy, is reduced if n increases. Ideally this EE is 0. Ideally this EE is 0 at Cn is equals to n. That means what? Ideally this EE is equals to 0 when EE tends to 0, when n tends to infinity. When n is equals to infinity, and this is going to be equals to integral f square of t dt, integral at t1 to dt f square of t dt, and this will be equals to this, and at n is equals to infinity, so that if this is x and this is also x minus x, it will be the 0, and so that point is named as it is complete set. Here the point is very clear. EE will be 0. EE will be getting reduced as n increases. If at n is equals to infinity, this term is equals to this term, so that if it is y and this is also y minus y will be 0. That means what? Ideally EE is 0 as n is equals to infinity. Under this condition, orthogonal signal set is called as a complete set or closed set. That means what? At what point this EE will be 0? EE will be 0. EE is equals to 0 yet n is equals to infinity. N is equals to infinity. At that case we can get what we can get? At that case we can get integral t1 to t2 f square of t dt is equals to sigma n is equals to 1 to n is equals to 1 to n Cn square into En. If these two are equal, this is equals to this is at n is equals to infinity, so that this minus and this will be completely 0 only whenever the EE is 0 as n tends to infinity. Whenever EE is 0, n tends to infinity, under this condition orthogonal signal set is called as a complete set or closed set. This is the point. Then we are going to talk about the another important thing, that is orthogonality in signal space, orthogonality in complex signals. In the next class I am going to talk about the orthogonality in complex signals, and the next one I am going to talk about the orthonormal signals. With this 80% of the second unit will be completed. Within 2 classes it will be completed. Complete second unit will be completed. Thank you, students.